All right, let's start. Do you have any questions? Okay. Yes, just give me a moment. Okay. So, um, so last time we were doing the axioms, right, of probabilities. So, okay, actually before that, right? So 2.2 was about the sample space, right? And events where basically we say, right, that the sample space is a collection of all outcomes, and then, right, events so you can call this S or omega, right, is collection of all outcomes. And then events, right, will be closed under complement. So if something is an event, then not something is also an event. And then, right, if you have a sequence of events, then the union, right, is an event. So this or that or that or that, right? As long as all of them are events, then you can combine them to be event. Well, these two together, right, would imply that the intersection of events are event, right? So this and that and that and that, so on so on and so forth are events, is an event. So basically, right, it just says that event can be combined using complement, intersection, or union, right? And 2.3 talks about then, right, how we can apply, right, probability on an event. So basically, events can be thought of, right, as the what do you want to say? You know, we can think of event as like the domain, right, of probability. So when we apply probability to an event, right, three things can happen. I mean, three things must be satisfied. The first thing is that a probability, right, is a number between 0 and 1. Second thing is that the probability of everything is 1, right? So I guess here I realized that maybe I have not used the right notation. So S is collection of all possible outcomes. That's the sample space. Omega, right, represents the event that something must happen, or the omega is a union of all events. So omega is the universe, right? Basically, is the universal event. So omega and S means different thing. Right? Something must happen. Right? The probability that something must happen must be one, right? So the third thing is that if you have events that are mutually exclusive, right? What that means is the intersection of any pair of events, right, is empty. Then if you look at the union, there will be the sum of the individual probability. And this can be a countable union, right? It can be basically an infinite union of event. As long as they're mutually exclusive, the law still works. But of course, right, I mean, if you apply it to a finite case, that's fine, right? Okay. So now from this, right, the consequences are the following. The first thing is basically that the probability of the complement of an event is 1 minus the probability of the event itself. 2, if an event is a subset of another event, right? This actually is the same as saying E implies F. Then the probability of E is less than the probability of F, right? Basically, if E implies F, if an event happening implies another event happening, then the probability of the first event must be no more. Oh. If first event is contained second event, then the probability of the first event must be no more, right, than probability of second event. The third one, right, is called the inclusion-exclusion formula. At the simplest level, right, it's going to be like this. At the most general level, it's going to be n events, right? If you have n events and you union them up, notice right here, the events doesn't have to be mutually exclusive. If they're mutually exclusive, then it's just a sum. But here, right, we're interested in events being in general. They don't have to be mutually exclusive. If that's the case, then first is a sum, right? And then you subtract the pairwise intersection. But right, be careful to only include once, right? You subtract, say, the pair 1, 2 once, and you don't subtract the pair 2, 1, right? You only do it once. That's why it's I less than j. And then you add back, right, the third layer. And again, right, here you only do it once for every triple. So on and so forth, right? And the last one will be minus 1 to the n plus 1, okay, of E1 up to En, which is all intersection. All right. So I think, right, we were in the middle of looking at an example, right, which is the so-called hat problem. And I believe that we were working with 3, right? So the hat problem says n people, right? N persons throw their hat together. And select one hat, right, randomly out of the pile, right? What we're interested in is the probability that no one gets the right hat. Okay, so the problem can be solved generally, and we will solve it generally. But to kind of make it a little bit easier to follow, let's just look at the case when n equals to 3. Okay, so whichever the number of persons, right? We still denote EI as the event that the ith person gets the right hat. Okay. And so the event we're interested in is probability of E1 complement, E2 complement, E3 complement, right? Because that would be the event that when n equals to 3, right, no one gets the right hat. And so here, right, the first thing we do is we use De Morgan's law, right, to turn it into a union. And then, right, use the first consequence, right, that we listed above to do this, right? The probability of a complement is 1 minus the probability of the event. And then, right, now use the inclusion-exclusion formula, right, to do this. Right, okay. And so I think this is where we stopped last time. Now let's fill in, right, the calculation for each of these probability. So E1 or each of the EI, right, represents the event the ith person getting the right hat. Well, if there are 3 persons or 3 hats, right, from the point of view of each person, there are 3 hats. And they're equally likely to be selected. So the probability that a person selecting the right hat is 1/3. Right. Now here, when n equals to 3, then E1, E2 is a bit special because, right, with 3 persons, if 2 of them getting the right hat, then automatically, right, the third person also gets the right hat, right? Of course, it's not true in general, but when it goes to 3, then if 2 persons getting the right hat, then a third person also automatically, right, guess the right hat. So each of these probability is 1/6 or 1/3 factorial, right? Coming from the fact that you know, out of 3 factorial possibilities, only one way for 3 persons to get the right hat. Of course, the last one is 1/3 factorial. Okay. And then we can simplify this expression to something which I'm not gonna write down, because what we're really interested in is a case for this formula, right? Same expression, sorry, same concept, but for general N. Okay. So I'm gonna let you work that out. So write down the general expression for okay. So basically work out this problem, but not when N equals to 3, for general N. What is the answer? All right. So for general N, right, then you still follow the same kind of approach, but at some point, right, you would have to use the general, right, inclusion exclusion formula. So first few steps are exactly the same. Right? But here we will use the general inclusion exclusion formula. Like so. Okay. All right. So now let's fill in these expressions. But now, right, we fill them in, I guess, generally. So what is P of EI in general? Again, general here, right, is for general N. And so the argument, right, is the same as before. That is, from the perspective of each man, there are N hats, each of them being equally likely to be selected. So each of the EI is 1/n, right? And because they're all equal and they're n events. So that's n times 1 over n. Okay, so that's that. Now let's continue to here. What would P of EI EJ be? What is this expression?
Are we assuming they're independent?
That's a good question. But first of all, can we assume independence? Okay, so first of all, it's not even covered at this stage, right? Which is, you know, sort of the reason, but are the events EI and EJ independent? If the first man gets their right hat, does that affect how the other person gets the right hat?
Yes, because there is a one less hat to choose from.
Yeah, I mean, in general, you can feel, right, that the action of a person will affect the action of the other persons, right? I mean, let's kind of turn things around. Suppose that the first person gets the second person's hat, so it's not getting the right hat, but getting the wrong hat. Then clearly the second person cannot get the right hat, right? Things like that. So yeah, the answer here is, right, we cannot assume independence, or in general, right? These things, it's not about can we assume, but if you even want to throw the word independence in there, you have to really analyze the situation and see, right, if independence is even there at all or not, right? But yeah, so two things to say here. The first thing is we're not even using it because it's not covered yet. And second, right, that the word assume doesn't apply here because we're not even modeling, right? We have to analyze the situation to see. And then here, EI and EJ are not independent because the action of one person will affect the action of the other person. All right, so how will we do this? Well, you do it simply by counting, okay? So again, right, what's our sample space? Or what's the size of our sample space? The size of our sample space is something over n factorial, right? Because there are n factorial ways, n factorial permutations, right? For the hats to be assigned to n persons. Agree? And they're all equally likely. So there are n factorial ways total for this to happen. Now, out of this, how many ways can happen so that the ith person and the jth person get their right hats? So suppose the second person and the nth person, right, gets the right hat. How many ways can that happen?
Only one.
No, because we're not saying exactly, well, it's not even only one, right? If the second person gets the right hat, the nth person getting the right hat, it doesn't say anything about what happens to the other person, right? We'll say the second person gets the right hat, the third person, n person getting the right hat, then it could be that the first person getting the right hat or not. It's all included, right, in that scenario. In other words, when you fix these two positions, every other position can permute among themselves. In other words, there are n minus 2 factorial way to do so. Okay. So that's probability of EIAJ for any IJ. Well, this of course simplifies to something, but we'll look at that later. So once again, right, this is an argument based on counting and equally likely, okay, events. So there are n factorial events, total outcomes. All right. And then out of these n minus 2 factorial outcomes would have, right, I and j having the right position or right hat, wherever you want, right? Because at the end of the day, you see, right, the hat problem is basically assigning n numbers into n positions and see if the numbers line up in their supposed position, right? Supposedly position. So is that okay? Now, how many pairs like this are there? When we say I less than j like this, how many pairs can there be?
N times n minus 1.
Yeah, n choose 2. That's correct. No, it's n choose 2. So you missed the 2 factor division by 2. N times n minus 1 would be all pairs when order matters. So 1, 2, and 2, 1 are different, right? So here is n. Oh, wait, hold on. Yeah, that's right, right. What you say is when order matters. That's np2. This is n choose 2 because we only, right, do I less than j. Or here exactly this notation means order doesn't matter. We only do it once. 1, 2, but not 2, 1. Okay. Okay. So I guess similarly, right, you can see this one would be PIJK would be n minus 3 factorial over n factorial. How many triples do we have? Well, we have n choose 3 triples. So on and so forth until the last one, which is just 1 over n factorial. Any question about this? Okay, but as you can see, this simplifies further. So let's write this down. 1 minus, this is 1, right? Now what's n choose 2? N choose 2 is n factorial, 2 factorial, n minus 2 factorial. And right, it turns out that a lot of things cancel. This cancel, this cancel, right? Similarly, n factorial, 3 factorial, n minus 3 factorial, right? For n choose 3, we have this. And so once again, right? And we see a pattern, right? 1 minus 1 over 2 factorial plus 1 over 3 factorial, so on and so forth, right? Until 1 over n factorial. And so now, right, we can just finish this to say this is 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, so on and so forth, until minus 1 to the n over n factorial. And that's the answer in general. Okay, any question? All right. So I guess the last thing to mention, but we kind of used it already, is 2.5, right? Section 2.5 talks about sample space with equally likely outcome. Right. And the only thing to say here is that if we have the sample space omega, right, or S, whatever, where we have, let's say, outcome number 1, outcome number 2, etc., right, outcome number n. So here I don't call it E, right, E for event. O is for outcome, which is, like I said, right, it's the smallest event possible. Then you see that the probability of each event, so each outcome is 1 over n, right? Because there are n outcomes possible, and they're all mutually exclusive, right, by definition, because they're smallest, right? They're smallest possible. So therefore, each of them is 1 over n. We used it here, right? You see? So in the hat problem, the n factorial outcomes possible, right? An outcome here being a particular way for the man to get their hat, right? So there are n outcomes possible, n factorial outcomes possible. And then, of course, right, the number of outcomes so that 2 persons, right, gets the right hat will be n minus 2 factorial. So the probability of that happening is this divided by total number of outcome, so on and so forth. All right, any question? So let's do some question. Let me see here. I guess let's look at question number 12, right? On set of prompts, which is in your homework. It says, so a school, right, which has students, right, and then there are three language classes. You have Spanish, French, and German. So any students can take any class, and they can take 2 or 3 classes together, right? So there are 28 students in Spanish, 26 in French, 16 in German. Okay. And then 12 in both Spanish and French, 4 in both Spanish and German, and then 6 in both French and German. Finally, 2 students, right, in all 3 classes. Okay. So question A asks for a probability that a student is not in a language class. Okay, so how will we do this problem? You don't have to say the exact answer, but what are they asking here? What kind of tool are we using here? So this, right, is exactly the hat problem in a way, right? Is exactly asking for the inclusion exclusion formula, because, right, if we let, let's say, S to be Spanish, F to be French, and G to be German, then the probability that a student not in any class is exactly probability of S complement, F complement, G complement, right? Which is exactly 1 minus P of S union F union G, which is, right, exactly 1 minus P of S plus P of F plus P of G plus P of SF, SG, FG, right? And this is an equally likely kind of problem. So a student, right, is equally likely to be in any this scenario. So P of S, for example, right, is 28 over 100. P of F is 26. P of G is 16 over 100, right? And then SF is 12. SG, sorry, 4, right? And 6. And then SGF is 2. All right. And whatever the final answer is, doesn't matter. That's the expression. All right. So question B was a probability that a student takes exactly one language class. All right, how do we do this problem? This question.
We could take a sum of all the students in one class and then subtract the doubles twice, subtract the triples, like in all three classes 3 times to make sure that we only have the single students.
Right, something like that, right? Yeah, so this is not something that is, let's say, presented as a formula. So you have to kind of draw out the Venn diagram yourself, right? And see how you would approach that. So I guess the suggestion is add up once and subtract twice, 3 times. That might work, right? I haven't checked that out. The way I would do it, right, is just to basically add up all these things, right? Make sure we do it once, right? So this is right. This is the area we want to add up, right? Because these are exactly the parts where they only are in one language class, right? So for example, the one that is only taking Spanish, right, will be P of S, right? Subtracting, right, P of SG minus P of let's say SF, and then right plus P of SFG, for example. So this is the one that only takes Spanish, right? Because you will subtract away the ones taking this, you will subtract away this, and then you add back. Is that okay? And then you would do the same thing for French. Right? And then you would do the same thing for German. Right. So I'm not saying that this is the quickest way or this is the only way, right? But what I'm saying is in this problem, you have to kind of write down, right, what you see that describe exactly, right, this region. So for me, right, what I would do is I just do it one by one, right? So I would do take this region, right, subtract away this, subtract away that, and add back this, right? But there could be some other approaches, right? And then just fill in the numbers.
Wait, sorry, why is the probability of Spanish, French, and German added and not subtracted?
You mean these things
No, like
or
the
which one?
last term in each of the yeah, yeah, yeah.
Oh, hold on. Maybe I did it wrong, right? So if I take this region, right, if I subtract away this, and then so basically, right, I want to. So okay, so
Oh,
here's how it works, right? Another way to look at it is like this. You can do that. Whoops. Right. So I hope this is going to be even more clear. So you take S, right? You subtract away SG, which is this portion, and then you want to subtract away only this part, right?
yeah, okay,
So this
I
part
get it.
is,
Yeah.
yeah, yeah. I mean, I think it just somehow the compensation works automatically in my brain, but right, that's how it works. And then of course, if you take away the parentheses, it's like this. And then of course, another way to explain is like if you subtract this twice, then you can double subtract, and you want to compensate once, right? Something like that. So is that okay?
Yeah, thank
So
you.
like I said, there's no single way to approach this, right? There's multiple ways. As long as you properly do not double subtract or double add, whatever, you'll be fine. Okay, cool. So see, um, if two students are chosen randomly, right? Two students, um, then at least one is taking a language class. Uh, so I guess I kind of abbreviate a little bit, but if two students are chosen randomly, what's the probability that at least one is taking a language class? How we approach this problem, this question?
For the first
So the
student,
first, yeah, go ahead.
for this first student, we don't care if they're in class or even in a language class or not. So we can choose any student out of n. So we have 100 students, and then we times that
Mm.
times the student who is at least one of them. So we can like uh do the inclusion principle where they're at least one class.
Not so sure, but is that even a probability? Ooh,
We
would it?
calculated the probability of not being in a class with
So
this picking two students and having at least one being in a class is the same as picking, or it's the complement of picking two students and neither of them are in a class. Right?
that's actually a good suggestion, right? So good. So the first thing is that somehow this sounds like it's related to this, but we'll see, right? So first of all, but someone recognized, right, that in fact, somehow this is a little bit easier being approached using the complementary principle, right? So this is one minus probability that neither student is in the class. That's actually the right observation, as you'll see, right? And it's not, as you will see, it's not really because we have calculated something, as I'll explain. But the reason is more along the line that there at least one student here, and which is why I kind of have some doubt about the first suggestion, whoever that said that. The reason is what? At least one means what? At least one means 3 cases, okay? First student doesn't take anything, student takes something, second student takes something. First student takes something, second student doesn't take anything. Both students take something. Does it make sense? That's what at least one means. So whenever you hear the word at least one, that means you list the cases from 1 to whatever. It's always easier when you deal with the at least something to deal with the complement side. I mean, of course, the complement side is smaller. So here, at least one, the complement side means none. So when you subtract that away, it's kind of easier to deal with because you don't have to list the cases. All right. On the other hand, here, how do we deal with this? Is it related to question A? I mean, it is, but in which way? Is it going to be whatever this answer is, square? So, any suggestion here? So the first thing, right, to note here is that, again, refrain from any independence assumption or whatever that is at this stage, because there's no such thing right now. And even if there is, right, you want to not even throw that in as as a reaction. So counting is always, let me say, a more robust way to do things, unless you have all the reasons not to. So if you proceed with counting, then what's our sample space, or what's the number of outcomes here? What's our denominator? Our denominator is 100 choose 2, right? Out of 100 students, we pick out 2 students randomly. So that must be how many ways to pick 2 students out of 100 students? Agree? Then what's our numerator? Our numerator will be something choose 2, right? Where this something is, that's called n, right? Where n represents the number of students not in any language class, which you can infer, right, from your question, from your answer in part A. Well, that's it. That's where the connection ends. We don't use the answer in part A in any other way than to glean the number of students not in any language class, to count the number of possibilities. So again, right, this is done purely by counting, nothing else, right? And this is, again, the equally likely, right, kind of principle. Out of 100 choose 2 students, right? There are n choose 2 students that are not in a language class. Therefore, right, this is the probability that neither students will be in any language class. And of course, right, that's also the complementary idea at work, right, where instead of counting at least one, you count one minus none, right? Any question about this? All right, let's continue. So the next one is number 15. What quiz are we on? Quiz 3, right? Which is about poker, right? Well, not that we need to look at poker in this class or anything like that, but for some reason, poker hand is like a classical question to ask when it comes to combinatorics, or discrete probability. So we just, follow tradition and do at least one problem in this kind of category, right? So if you are not familiar with, cards, right? A deck of cards has 52 cards total, right? With 13 denominations, which is, right, doesn't really matter, but 2, 3, right, up to 10. You got Jack, Queen, King, Ace, right? So 13 denominations. You have 4 suits, right? So 13 times 4 is 52. Which is what? Spade, heart, club, and diamond, right? Okay. So that's it. That's the possibilities, right? So you have 2 of spades, 2 of heart, jack of club, jack of diamond, whatever, right? So a poker hand, right, consists of 5 cards, right? So 5 cards select out randomly, let's say, out of 52 cards. So everything here, right? And we ask for the probability of a certain kind of combination. So everything here will be divided by 52 choose 5, right? Because that's the number of ways to select 5 cards out of 52 cards. The question is, right, what to count so it's really a combinatorics question, right? To count the possibilities of whatever combination we describe on top. So part A is a flush, right? So again, that's the word from poker, which just really means that all cards have the same suit. Right, so what's the probability of that? How many ways can we select 5 cards of the same suit?
Thirteen choose 5.
So is that it? Times 4, right? Because there are 4 possible suits. All right. be one pair. Now this one is slightly harder because notice that one pair means that exactly one pair, okay? So if you're not careful, oh, by the way, one pair means something like, let's say, 2-2, and then ace, jack, and king, right? Something like that. That's a one pair, right? The reason is if you're not careful, you might include the second pair in here or another pattern, like one pair and then three of a kind, which is a full house, right? So this is a one pair only. So nothing else, like no other patterns. In other words, right, all three cards must be different. What would that be? Well, so the first thing, right, is to decide which pair it would be, right, among the denomination. So there's something like 13, choose one, right? Which pair would be, right, out of 13 possibilities. And then among the four cards, you choose two to be your pair, right? So this takes care of the pair. Then what else? The remaining cards, right, must be not from the same denomination. So that's from the remaining 12 denominations. But then, right, you need to make sure that they each come from a different denomination. So that's 12, choose 3. Right, so from the remaining 12 cards, you pick out 3 cards, right, to be these cards. And then they can be any kind of suit. So 4Q. All right, any question about this?
Can you go over this just once more, please?
Sure. So the pair, right? How would you get a pair? You get a pair by picking, right, one of the denomination to be a pair, right? Let's say you want to have a pair of A's, whatever. So there are 13 ways to do so, right? It's 13, choose 1. And then once you decide on the denomination, then you need to choose which cards to be the pair, right? There are 4 aces. Which one? Therefore, 4, choose 2, right? So together, this is the possibilities of the pair. But once you settle that, then you need to decide on the remaining cards. Now, the remaining cards must not be the same as whatever you chose to be a pair. So out of the 12 remaining denominations, right, you choose 3 denominations. Notice that this also takes care of the fact that they must be different denominations, because 12 choose 3, right? So you would pick 3 different denominations out of the 12. But then, right, each denomination can come out to be 4 types, and that's allowed. So that's why it's 4Q. Is
I
that
got
okay?
it. Yeah.
C, 2 pairs. And this probably is slightly easier. So 2 pairs, right? Something like, let's say, 8, 8, queen, queen, and then something else, right? Like a 4. What would that be? So you want 2 pairs, right? So what must you do first? Out of the 13 denominations, pick 2, right? To be your pairs, to be your 2 pairs. Each of these 2 can be of any kind of suit. So that's square. Okay, so far. So that right, takes care of the 2 pairs. And then the last card, right, must come from the remaining 11 denominations. Each of them have 4 possibilities. So 11 times 4. Or, like 44 cards, right, remaining after you kind of selected your pairs, which is the 8 cards, right, from the 2 pairs. Any question? All right. D, 3 of a kind. So 3 of a kind, right, also must be exactly. The reason is because, right, you want something like 8, 8, 8, right? But then the remaining cards must be different, like an ace and a king, right? Because if you're not careful, you can include the last card being the same, which is 4 of a kind, or these 2 cards being a pair, which means it's a full house, right?
So is it 13 choose 1 times 4 choose 3
Mm-hmm.
times 10 choose 2 and then 4
Not 10, not 10, not 10. 12, right? 12 choose 2.
oh yeah,
Because you only have one denomination, yeah. Times,
times 4 square.
correct. Mhm. Any question? All right. E, 4 of a kind, which means something like 8, 8, 8, 8, and then the last card can be something like an ace. How many ways?
Something like 13 choose 1 times, I guess, times 48
That's correct. 12 times
choose
4.
1.
That's correct. All right, we're good. So again, it's just an exercise in counting more or less. And again, it's nothing to do with cards. We're not gonna particularly do cards in this class, but it's somehow a traditional question that's always asked, right? When you do combinatorics, it's kind of fun. So, all right. Okay, let's continue. Let's look at, so this is quiz 3, quiz 4. This is question number 25. It says that a pair of dice is rolled until a sum of 5 or 7 shows up. Find the probability that a 5 occurs first. So it's basically a 5 occurs before a 7, right? So this question, right, is probably a little bit complex if you're new to this subject. The first thing you probably want to look at is what is your sample space. What are all the outcomes here? What are we dealing with? And this is, I think, connected to question number 2 assigned on your homework, which I'm not going over right now, right? But a similar thing. So it has a case of like, you keep doing something, you keep doing your experiment until something happens. So what's the sample space? So your sample space, right, is a collection of, let's say, sequence that basically, I'll just represent them as x's, right? Like that, okay? Where what happens is that all the rows before are not 5 or 7. Okay, so I mean, when you roll a dice, right, a pair of dice, you might as well think of it as like, you know, have something that has 36 possible outcomes, right? And then 5 or 7 are one of those possibilities, right? Out of, sorry, not 36, right? Because you look at the sum, so 12 possible outcomes, sorry. But notice that if we look at them as 12 possible outcomes, then, right, these outcomes are not equally likely, right? A 5 is not the same as a 7 in terms of the probability. But anyway, right? So basically, we're looking at outcomes that not 5 or 7, not 5 or 7, and then end at 5 or 7, right? And this is a sequence of n, length n, right? So what I'm trying to say here, right, is that these are all outcomes you're interested in, right? Because you are rolling a dice until you see 5 or 7. So you never know when that happens, right? You just know that you roll until at the end you see 5 or 7. So that's going to be your sample space, okay? So several things to note about this sample space. And the first thing is this is infinite, meaning that, right, you don't have, it's not a finite sample space, right? You can keep on going forever. And being infinite sort of implies that the sample space is not equally likely. Right? Because if they're equally likely, then each outcome will have the same probability multiplied by infinite, not gonna work, okay? So I guess I'm saying this more in reference to question number 2 in the textbook, in your homework, rather than this problem. But either way, right? You should be aware that this is what you're working with, right? An infinite sample space, okay? The textbook, right, would hint that, so out of this sample space, you look at the event, En is that a 5 occurs on the nth row, and no 5 or 7 occurs on the first n minus 1 rows. Right, which is kind of like what I'm trying to describe here, but it would be more specific, right? It will be, instead of end up with a 5 or a 7, you want to end exactly on a 5. What's the reason? The reason is if you end with exactly a 5, that means a 5 appears before a 7. Is that okay? So it's sort of like a sub-event of this, right? Here you look at all tosses where 5 or 7 occurs. So I guess not a sub-event, but basically here, right, there are 2 possibilities. X, 5, X, 7, right? So these are the possible outcomes. Is that okay? So I guess the 5 or 7 here is like a lazy way to write that. Now, En is the ones that end up in the 5. Because then, right, the 5 will occur before a 7. Is that okay? And then, right, the event we're interested in, the probability we're interested in is probability of the union of En from 1 to infinity. Why so? The reason, right, is because you can see, right, what does this mean? This means that a 5 occurs on some row, right? Here you allowed from 1 to infinity, and 5 or 7 did not occur before those rows, right? Here n can be 1,000, n can be 10,000, whatever. And again, right, this is connected to the fact that your sample space is infinite. You can keep on throwing, right, like 999 throws, and you never see a 5 or 7. That's rare, but that's possible. And then, right, you see a 5 or 7 on the 1,000th row, right? So that's allowed. And so this union reflects that. And then, right, we notice that the En here are mutually exclusive, okay? they're mutually exclusive basically just from the fact that, you know, the length of the row is different, right? E8 and E9 has nothing in common, right? E8 means that on the 8th row, right? E8 means that on the 8th row, you got a 5, right? Because a 5 occurs on the 8th row. On the other hand, E9, by definition, must means that a 5 or 7 does not occur on the 9th row, on the 8th row. Because, right, a 5, 7 does not occur on any of previous row. So that's why they're not, they have nothing in common. Which explains, right, that by the axiom of probability, we can sum this up. Okay, like that. So, I mean, a lot of these are pretty obvious when you just look at the language. I'm just trying to explain the setup of the whole thing, right? Let's say with the axiom of probability in the background, so you can see how this kind of fit into the whole probabilistic framework. But in the end, right, it's really boiled down to calculate this and then sum it up. And again, right, be very mindful that no such thing as independence comes in here. So how would we calculate the probability of the EN? All right, so the EN, right, it sits in what kind of sample space? How many possibilities are there for us to do n rows of a pair of dice? How many possibilities? If we roll a pair of dice one time, so by the way, right, these 12 outcomes or 12 events I'm referring to are not equally likely. But as you can see, right, equal outcomes are the only tool we have right now to calculate probability. So a pair of dice has 36 possible outcomes, right, that are equally likely. 1, 6, 6, 5, whatever, right? So if you roll it n times, then it's 6 squared raised to n. That's the number of outcomes you have, right? And now, right, what are we interested in? We're interested in the outcomes where a 5 occurs on the nth row, on the last row, and a 5 or 7 does not occur. Sorry, like does not occur, right? On the previous one. Okay. So how many ways can this happen? Well, how many ways out of 36 possibilities for a sum of 5 to occur? A sum of 5, right, comes from 1, 4, 4, 1, 2, 3, 3, 2, right? So that's 4 ways for the last possibility, for the last row, 4 possibilities. For the previous ones, right, we don't want it to be a 5 or a 7. So how many can that be? So this is, right, the sum of 5, right? Well, sum of 7. Well, you have 1, 6, right? 6, 1, 2, 5, 5, 2, 3, 4, 4, 3, right? So there's 6 ways. So 6, 4, so there are 10 ways total to get a sum of 5 or 7, right? So there are 26 ways total to not get 5 or 7. So that's 26 raised to n minus 1. Is that okay so far? And again, right, notice that I'm not using any independence or anything like that. It's just pure counting, right? There are 36 possibilities for each row raised to nth power for n rows. Out of those 36 possibilities, 26 of them do not result in a 5 or 7 as a sum. So I raise that to n minus 1 power. I want the last row to be a 5, in which there are 4 possibilities. Are we okay? And now, right, it's just going to be a manipulation of a geometric sum. So here we'll factor out 4 over 36 to kind of make the power to be n minus 1, right? And then if you do that, it's going to be 1, right? The first term, which is 1, because 1 minus 1 is 0, so 1 divided by 1 minus the ratio. So we get 4 over 36. This is 10 over 36, so 36 over 10, ending up in 4 over 10. That's the final answer. All right, any question? Okay, so I think that's about to cover, right, all the probability questions in your homework. I mean, we didn't talk about all of them, but at least kind of the interesting ones. So now let's continue to some other questions not in the homework. So this is quiz 5. This is question number 27 in the text. It says, an urn contains 3 reds and 7 black balls. Players A and B take turns drawing balls, right? Drawing 1 ball from the urn until a red ball is selected. So find the probability that A draws the red ball. So here, right, A goes first. Okay. So also, I guess they say no replacement or without replacement. So I guess we can put that in here. Okay. So I guess the first thing to comment on is, right, when drawing balls out of an urn for some reason is a very typical probability question, in at least in discrete probability, right, or combinatorics. But when you draw balls, there are two options. You can draw a ball, observe it, and then put it back into the box or the urn. In which case, right, that's called drawing with replacement. Notice, right, the effect of drawing with replacement is that the size of the urn, right, the size of the composition never changes because you draw it out and you put it back. But when you do without replacement, that means you draw the ball out, right, and you observe and you don't put it back in, right, you just keep it somewhere else. The effect of that is that the composition will change, right, along the way, depending on how you pick the ball, right? So that's with or without replacement. Okay. And so again, right, with any kind of probability question or even combinatorics question, you want to imagine what's going on. Okay. So I guess the context is clear, right? A goes first. So A can be lucky and draw a red ball, in which case, right, that's done. Or A can draw black, right? B can draw black, and then A can draw red, in which case it's also done, which is right, this kind of scenario. But we can have A draw black and B draw red, in which case it's also done, but that's not part of the scenario, right, that we want. Things like that, right? So the question is, in all the scenarios, right, what's the probability that A would draw a red ball? So for these questions, there may not be a quick answer, right? It's not like a small short answer. Don't always look for that. For example, right, something like this requires you to write down a sum, sum things up, etc. Right? So it could be that you have to list out the cases, in which case you just do so. All right, so let's ask. For example, right, this first scenario, A draws a red ball on the first pick. What's the probability of that? A draws a red ball on the first pick. Probability of that is 3/10, right? And then if not, what should happen? If not, the next scenario should be this, right? Black, black, and red. Correct? And these are mutually exclusive, so we can just add them. So what's the probability that we will draw black, black, and red in that order?
Seven tenths times 6/9 times 3/8.
Uh-huh. 7/10 times
6/9
6 over 6/9 times
3/8. Yeah.
All right, so I guess this is correct, but what principle are you using to do this?
I just counted.
Okay, count is good, but are you sure you're not slipping in any independence in here? I'm just asking what you're thinking of. Is it done via counting, right? Or is it done via independence or whatever you're thinking about? Because what does this timing means? Because you're multiplying probabilities together, right? At least that's the way you read it.
Oh, so
we
do we
have
have to divide it by a third to make sure it's no times 1/3 factorial to account for the
No,
right
no,
order?
okay, so you see, that's what I'm saying. This is correct, though. I don't think this is wrong. But notice that the way we operate so far, it would be the number of ways something happens divided by the total number of ways. Okay, that's done by counting. Counting is that. The way you're reading things up, you're really looking at the probability of drawing the first black, the probability of drawing the second black, the probability of drawing the third red. Is that right? And then you multiply them together. So the taste of this is you're multiplying probabilities, which somehow is related to independence or conditioning. I mean, this is correct using conditioning, so it's not independence even. What I'm trying to say is, like, do you even realize what approach you're using, right? Just so that you know, because these things can be a little bit confusing. So the way, so it's kind of, it's a little bit pedantic here, but right. So here, the way I would prefer to see it done, even though the numbers are the same, is that it's 10 times 9 times 8 over 7 times 6 times 3, like that. Is that okay? So basically, right, 10 times 9 times 8 represents the total number of possibilities that you can draw the first ball, second ball, and third ball. And by the way, this already takes into account order, because that's 10 choose 3 times 3 factorial. Is that 3 factorial you mentioned? Is that okay? And then 7 times 6 times 3 are the number of ways we can draw a black ball on the first way, on the first turn, another black ball on the second one, and then a red ball on the third. Is that clear? That's counting. This is stringing together probability. Again, in the end, they're all the same. But right now, we don't have a principle to cover this calculation because you're multiplying probability together. Is that okay? All right. So that's the black, black, red, right? What's the final one? Black, 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 red, right? That's it. Because that would be, hold on. So, yeah, right. This is the third way that can happen. So you can have 6, right? Like that. Am I right? And that's it, right? So yeah, so we need to account for these two possibilities, right? So the next two will be what? What about this? This will be 7 times 6 times 5 times 4, right? Times 3 over 10 times 9 times 8 times 7 times 6, right? Is that okay? That's this one. And then finally, you have 7 times 6 times 5 times 4 times 3 times 2, and then times 3 over 9 times 10 times 9, 8, 7, 6, 5 times 4. Are we okay with this? Any question? So again, right, I don't think, I'm not so sure there's a quicker way to this problem. The nature of the problem, right, because players take turn, etc. Sort of seems like we have to kind of go through and list the scenarios. And again, right, we want to do it by counting. So we need to list out all the possible ways that we can pick out the balls. And then, the numerator will be the ones that we actually are interested in. All right, are we good? Okay. So let's do another one. This one is slightly less weird. So question 6. This is question number 28. So an urn contains 5 reds, 6 blues, 8 green balls. So a set of 3 balls is randomly selected. So again, right, in this language, and I guess by default, I'm just saying this so that if you don't see anything, this is without replacement. So when people say a set of balls are selected, unless they say something else, is without replacement, okay? So then question A is, what's the probability that the balls are of the same colors? All right. What's the sample size here?
Three.
I guess I didn't hear the first word. What, 3?
Oh, I thought sample size was 3.
Sample means, sorry. No. Sample size is not the number of balls selected. Sample size is how many possibilities are there. Right? Namely the denominator that we're dividing by.
19, choose 3.
Correct. And out of these, right, what are we interested in? Balls are of the same colors, right? So how many ways can we do that? Choose 3, plus 6 choose 3, plus 8 choose 3. Understand what that means, right? Either all reds, all blues, or all greens. Is that okay?
Quick question. So the plus indicate or, right?
Yeah.
Okay.
That's correct.
If it's multiplication, that would be and.
Generally, I mean, again, yeah, I mean, sure. I mean, because that's coming from the multiplication principle, right? A choice from this group and a choice from that group means we multiply together, right? Yeah. B, yeah, probability of the balls are from different colors. What's the probability?
Is this asking that each individual ball is different, or like can 2 of the balls have the same color and one of them is also different?
You're right. That's a good question. I think that's only the word in the problem, from which I think the interpretation is each individual ball is different, I think.
Okay, thank you.
Okay, so the answer is? The answer is?
5 times 6 times 8.
That's correct. Is that clear? Because we choose one ball from each group, right? C, repeat A and B, but now with replacement. All right. So now, how would the answer be different if we do it with replacement? Meaning, after we take the ball out, we look at the color and we put it back in. So first of all, right, let's look at question A. Or let's look in general. So what's the sample size now? What is the sample size?
19 cubed.
Exactly, right? That's the first thing you should recognize. Its sample size now is 19 cubed rather than 19 choose 3. Very good. So then what's the numerator?
5 cubed plus 6 cubed plus 8 cubed.
Correct, right? I think that's the way. Because each time we pick, right, we must pick from the same group. And then so that's the number of ways we can do so, right? What about probability of different colors? What's a numerator?
Still 5 times 6 times 8.
Exactly, right? In this case, it's still 5 times 6 times 8. Are we okay? Any question? All right, so let's do one more. Quiz 7. And this is question number 39. They say there are 5 hotels in the town. If 3 people check in to hotels, right? What's the probability that they check in to different hotels? Does that make sense? Because, right, I mean, 2 people can randomly somehow check into the same hotel, right? So, I think for some reason they say, what assumptions are you making? But let's just also correct it. I guess it's more important, this one. So how do we solve this question? So this question, right? I think sometimes it's described as like some in other contexts as like you have so many boxes, right? So here, of course, you have 5 boxes. And then you drop, right? So you have so many keys, you drop them into randomly into the box, right? You have your keys, you just choose a box randomly to drop them in. And of course, right, if you have a key in there, if you have another key to drop in, is called clash, right? Basically, you know, if more than one key is dropped in the box, is called clash, whatever. So what's the probability that no clash happened, whatever, right? So something like that. So you have boxes and you drop objects into a box. But notice this also has a taste of like something like width replacement, because a box can be used twice, right? So anyway, so that's just a comment on the taste of the question. But how do we answer this question? What's the sample size? That's always the question you want to ask, right? What's the sample size?
Five cubed.
Excellent, right? That's exactly what I was saying about the width replacement, right? 5 cube, right? And where does 5 cube come from? Each person, right, has 5 choices, right, for the hotel. And it can be repeated, right? Because the second person doesn't have to avoid first person choice. So 5 cubed, right, for the sample size.
okay, for the total number of choices of each of the individual. All right. Now, what's the numerator? What are we interested in?
5 times 4 times 3, which is ways
Yeah.
to choose different hotels.
Exactly right. That's exactly that. There you go. Are you okay? So that's the answer. Now let's finish with this thing, right? What assumption are we making? So it's not super important here, but we are definitely doing something like equally likely, right? Meaning that all the choices, right, out of 5 cube choices, they're all equally likely. So you can say something like the hotels are not in any different preference, right? For example, for some reason, there's a hotel that's really strongly preferred generally. Then the division by 5 cube, right, would probably not be true because people will sort of, right, go to the same hotel, right? Another one, which is sort of like the independence assumption, which we avoid mentioning because we're not covering independence here yet, is also in the air, right? Which is kind of reflected in 5 times 1 times 3, because basically if these guys know each other somehow, right? Or if somehow they try to avoid each other actively, then the fact that the first guy has 5 choices will somehow influence, right, the second one. Or basically there will be no choices, right? Because say they're all friends, then there's only one choice because they all will, or there are only 5 choices, right? Because they all will go together, right, into one hotel. Or if they actively avoid each other, then already there's, whatever, right? So I'm saying there is the equally independent assumption, sorry, equally likely assumption, meaning the hotels are all similar in some way. And then there's also the independence assumption, but you don't have to throw that in that way. You just say the action of one man does not affect, right? The choice of one person does not affect the choice of the other person, things like that, right? So it's sort of like all implicit in this calculation. But all right, so I think that's enough for today. If you have any question, I'll answer them. If not, I'll see you next Monday. Okay.
Professor, I had a question.
Yeah.
In quiz number 5, question number 27, you mentioned that 7 times 6 times 3 over the sample space already accounts for the order. But since it's multiplication, how does it account for the order?
Yeah. Let me pull it up real quick to
Yep.
see what that is.
It was when we were drawing like 3 red and 7 black ones.
This one, right?
Yep.
Yeah, because I mean the clearest one is to look at 9 times 10 times 9 times 8, right? We recognize from something like 10 choose 3, right? For example. But if you do 10 choose 3, notice that it's going to be 10 choose 3, 10 times 9 times 8 over 3 factorial. Agree? That's 10 choose 3. So in fact, right, 10 times 9 times 8, or someone in class, I'm not sure it's you or someone else, refers to the answer I was asking with, I forgot what I was asking. I asked maybe 10 choose 2, and the person say is 10 times 9, right? Whatever. But I mentioned that 10 times 9 actually will be a permutation number because you already multiply 2 factorial in front, right? So in fact, 10 times 9 times 8 is referred to as 10p3, right? Instead of 10c3. Does that make sense? So that's the and also another way you can think of it is like this. The 10 clearly comes in the first turn, the 9 in the second turn, the 8 in the third turn. You multiply it like that. So you already built the order into that counting.
Yeah.
Does that make
But
sense?
what about the numerator? So 7 times 6 times 3. Would this also account, for example, for like our choice of having the first one as red is 3 out of 10. So wouldn't that be literally the same thing, like 3 times 7 times 6?
No. So, okay, the top also has an order built in because here, right, we clearly mean the first choice, the first draw has 7 choices of the black. The
Mhm.
second draw has 6 choices of black. You
Mhm.
see, because basically what we're doing here is the multiplication principle. And the multiplication principle says so many choices on the first group, so many choices on the second group, so many choices on the third group. So in a way, the multiplication principle has order built into it. If you know, right?
Okay.
The factorial, the n factorial is built out of the multiplication principle, right? Do you notice? So
okay.
to do this, right, we already say the first term must have 7 choices, etc. Right?
Mhm.
Yeah.
Okay, got it. Thank you so much, because that was like, I was bugging me while I was thinking of it. Thank you very much.
Professor.
Yeah.
I sent you an email about the first quiz a while ago. I was wondering if I could get credit for it because the reason I didn't submit it on time is because I stayed late to ask a question.
I may not have received your email. You sure you send it to the right email?
Oh.
I don't recall because
Okay.
I would have responded.
I'll resend it.